Now we're going to talk about using your calculator to check your answers in the calculus paper. Now, you still must use calculus methods for every question. You must have a differentiation and anti-differentiation step. It's often quicker to check your answers using the calculator than it is to rerun through the working. First up, finding a gradient at a point. There's actually a function for that. In your run options calculus, you select ddx, enter the original function, a comma in the x value, close the brackets, and the result is the gradient at a point. So we'll have an example. For this function, fx is 0.2x cubed minus 5x. What's the gradient at 5, 0? Well, normally we would do it. We would differentiate our function. 0.2 times 3 is 0.6, and x cubed becomes x squared. X to the power of 1, 5 times 1 is 5, and then x drops away. So our gradient function is 0.6 x squared minus 5. And to find the gradient at a point, we need the x value at the point. Well, we're told the x value is 5. Now, we don't need to worry about the y value because that doesn't have anything to do with it. X value is 5, and we put that into our gradient function. The gradient function at 5, 0.6 times 5 squared minus 5 is 10. The gradient is 10. Now, I want to check that, and so what I do is I go into Run, Options, Calculus, and then F2, which is ddx, because ddx is differentiation, and I type in the original function. Very important, the original function, 1.2x to the power of 3 minus 5x, and I'm doing it at x is equal to 5, close my brackets, and there's my answer, 10. Run, options, calculus, ddx, type in the original function, 5, get my answer, 10, and that's good because that's the correct answer. Now you can check turning points the same way, except that it doesn't give you the y value at the time, it only gives you the x value for your turning points. So we can do that graphically instead, and to do that we take our function, enter it, and draw it. So in graphs, I've already entered one, x minus 1 squared, and I draw that. Now if I want to find the maximum, gsolve max. So the maximum is at x is equal to 0.33333. Now that is almost certainly a third, and there's my y value, 0.148148. Got to be a little bit careful. The calculator works by approximation. If we go gsolve minimum, then it finds x is equal to 1. It tells us y is equal to 5.59 times 10 to the minus 23. So that's 0.22 noughts 5, and that is in fact obviously 0. Just be a little bit careful. Calculator only works by approximation. It's a good check, but it doesn't do the thinking for you. So that's our procedure. We go F5, gives us the gsolve menu, max gives any local maximums, min gives any local minimums. There is a problem, and that is that the graph function doesn't work very well outside the visible range of the graphs. We'll have a look at how that works. If I exit out from this and I make my graph x minus 100 squared, and I enter that and to draw it, then it's not visible anymore. So when I go gsolve max, it doesn't find it. If that's the case, then one solution is, when you've drawn it, to re-change the view window. So I go to view window, and I'm going to change the max. So I now know it's going to be a long way to the right. I can actually change the Y scale too if I want, but it's not necessary, it searches through the X range. So I enter that, and when I draw it, still can't see it, miles out the way, but I go gsolve max, this time it finds me my max, 33 and a third, and my y is 148, blah blah blah. So can find it, but only if your selected visible range is in the right X region. It doesn't look outside that region for local minimums and maximums. You need to know how to use the view window function to extend the visible range. The great advantage of that is that you can also check any y values. So if we go back into that and I enter trace and 56, then my y value at 56 is, I go trace minus 2, no, trace minus 2, and it tells me my y value, x equals minus 2, y minus 20,808. Very effective for very awkward calculations, especially when you've got fractions. I'll just change the function back to something more visible so we can actually see what's going on. Right, and change my view window to standard. Right, now one of the great advantages of trace is that if I select trace and enter 2 ABC3, I don't have to do anything with calculator fractions, and I get the answer, 2/3, and a very accurate answer for it. Same also, when you've got ones like this and it's negatives, you can use the trace function to solve awkward ones like minus 3 ABC4. Many of you aren't very good at solving those. So that gets the exact answer you need using the trace function. Very useful. You enter your x value, it will return the matching y value. It's very useful when you're checking higher powers, awkward fractions and negatives. Again, you can have to extend the view window function. The view window function to extend the visible range. You can also use it checking tangents. We can see that a function is a tangent to a curve. So we'll have a quick check of that. In this graph here, we'll exit it out, we'll change it, we'll make it x minus 1 squared, and we'll check whether 2x minus 3 is a tangent. I draw it, and I can see pretty quickly that it looks very close to being a tangent. You've got to be a little bit careful. It doesn't always meet. I can go G-solve and see if they intersect, and in this case it does. It doesn't always happen because sometimes the approximations mean that it misses. So you can use the function, draw it, and then view it. I don't advise using intersect because it often misses. Then you need to have the view window correctly solved, but at least you should know where it is before you start with a thing like that.